always start to refresh ourselves what we learned before. Is that yesterday we spent the majority of the whole class realize, okay, forget about the Lie groups. It has way too many elements to count. Then we should just focus on the Lie algebra, which has, n generators, and they come with a structure constant. And then we learned these structure constants are very powerful. They basically describe everything we want to know about the group. And we don't really need more information. And that's all we need. And these guys are real and completely antisymmetric if it's compact, if it's coming from a compact Lie group. And they also follow Jacobi identity, just because they are commutators. And this last property is very useful because this tells us for any Lie algebra, we always have at least one non-trivial representation, which is the adjoint representation. And we can show that through the Jacobi identity, indeed, these guys will furnish a representation of the Lie algebra, that is to say that they satisfy this commutator relationship. So that's where we ended yesterday. Is there any questions? All the questions will probably pop up in today's tutorial. Or yesterday's tutorial, if after I post to the solution. Okay, so now, see, we're in trouble. We don't have many lectures to go. And if our goal is really figuring out how to write down all the representations for all the Lie algebras, and there's probably there are definitely infinite number of Lie algebras because they are labeled by natural numbers, and it has at least like 3 theories of them. And then if that's our goal, it seems hopeless. It's a mission impossible. Even if I can write down a representation for a Lie algebra for you every single minute, I'm going to running out of time very soon. So what do we do? Well, let me tell you this. The hope is not lost. And actually, let me try to emphasize this, that while you're growing up, you might have heard about this rumor that OB1 is our only hope. So let me tell you that you have been lied to. This is not true. Okay, this is a lie, and not to be confused with Lie group. And you might also have heard that R2, D2, wrong index, is our only hope. And this is also wrong. And now you know that why I spent a whole lecture teaching you what is a D2, right? But this is wrong. Okay, and we'll use the entire lecture to show that SU2 is our only hope. And this will become more and more clear when we get the end of the lecture that we are trying to get everything into SU2. So I hope this is a good proof that SU2 is very important. Okay, so let's get started. And we'll take however long to write down literally all the irreducible representation of SU2. And if we're ending class early, then we'll end it early, because I really want this lecture to be entirely on SU2 and nothing else. And from Monday, we'll try to teach you everything that I have otherwise in mind. So let's get back to our beautiful Lie algebra. Well, there are several reasons besides the fact that that SU2 is very important. There are other reasons that people really want to study SU2. Is because if you stare at the structure constant and you say, oh, FABC is completely anti-symmetric. There's something we do know that it has, several indexes that they are completely anti-symmetric. And what would be that? Epsilon. Right, this Levi-Civita symbol that we all can define in any dimensions, but this is indicating we're defining it in 3 dimensions. And then there's this thing says we take it to be, I guess, 1, or if we take any even number of permutation, that would be 1. And if any odd number permutation will be -1. And this thing is certainly anti-symmetric as we construct it to be. Right, so then SU2 is indeed says we have exactly 3 generators. You can't quite go down like from there. You need a commutator relationship, and they are completely anti-symmetric. The minimum generators that make it non-trivial is 3. And if we have 3 generators and the structure constant is given by epsilon, that's indeed our SU2. And for some reason, it's usually labeled as J. And I hope that it reminds you something that you learned from undergrad. It looks like. No? Angular momentum. Good. So then you might have heard about this angular momentum or spin. They are quantized somehow. And then today we'll, along the way of looking for the irreducible representation of SU2, and then we'll illustrate why we think this thing is quantized. It literally have to be. Okay, so this is our focus. When we say SU2, we meant this thing. And before we get started, it's good that, if we have some general recipe to look for, let's call it the representation hunting. Okay, so suppose I have a Lie algebra, which is a bunch of generators and has commutator. They say the step 1 would be, which makes sense in physics. Remember, these generators are Hermitian, so they are in principle observables. And for observables, we like to mutually diagonalize some of them. Like if they are mutually commuting, then we can mutually diagonalize them, and then we can call the eigenvalues some observed things. So the first step is find the maximum set of generators that mutually commute. So we have a set that has H1. Okay. It has T1, T2, and da. And we want to achieve that all the commutator within this subset that they are commuting. Okay, sorry. Let's use the notation everybody use, that if you are chosen to be this special subset, and people sometimes use H, and this set actually has a name, and it's called the Catan subalgebra. And the Catan subalgebra is very important, although the algebra itself is completely trivial. Since anything belongs to this subset, they are mutually commuting. And anything mutually commute them should be added to this subset, so it should be a maximum subset. And the number of the generators gets to make it into the subalgebra, or the dimension of this is called the rank. As you see, we go up in rank, we become more and more complicated and sophisticated. And for SU2, how many members are there in Catan subalgebra? One. Cool. We indeed started with the easiest. There's rank 1. Well, that algebra tells you that anything else, if you put anything else, then the commutator is obviously not 0. All right, so we can pick anything we want, but to agree with what we learned from quantum mechanics, we're going to pick J3. So the Catan subalgebra of SU2 is quite simple. It contains one element, which is J3. And this is going to provide us the observables. What do we do with the rest of the generators? A good question. That's the next step. Step 2 is we're going to organize the rest of the generators. By linear combine them such that they become eigenvector of the Catan algebra. And the eigenvector is defined in this equation says that okay. So there's some linear combination of the generators. We'll label it with alpha. Okay, let me not label anything. Let's just say it's something which is the linear combination of the rest generators such that the commutator of the Catan subalgebra with them will be yielding at a constant and this guy again. So there's some unspecified object, and the property of this object is the commutator of this object with the thing in the Catan subalgebra gives itself back with some constant. So this is like an eigenvalue problem, especially if you remember our generators from the end of the last lecture is that they are actually some sort of basis in the vector space. So if you write it in that notation, this is literally says HI acting on this vector gives some constant back and this vector back. So it is literally an eigenvalue question. So what we wanted to do is organize all the other generators that didn't manage to make into the Catan subalgebra into the eigenvectors of these special ones. Okay? And then step 3 is that there is a method called the highest weight method. Okay, this I have no idea why they're called a weight, but the weight is really just another name for eigenvalue. To build the irrep. So what exactly do we mean by building a irreducible representation? Remember, the representation is just matrix, some matrix that represent the generators. And then we'll exponentiate and get everything else. So if it's a matrix, what we mean by building the irrep is really say, let's find the vector space, which is of concern of people yesterday in the tutorial, says what does it act on? Exactly, we're going to hunt for this vector space. So to build the irrep, the important part is actually find the vector space, and after we find the vector space, then we look for the matrix element, how these operators, the generators will act on this vector space. And by construction, we already know how this Catan algebra, subalgebra will acting on the vector space. It's diagonal. So we already built one. As soon as we find the vector space, we already know the representation of the Catan subalgebra. And now we'll try to find the rest. Okay, so let's get started with SU2. Step 1 is already done. We have 1 that is special, which is chosen to be J3. J3 is special. Okay, and next step is to do linear combination of the rest of generators. This can get crazy when we have, more than 3 generators, so you don't know like how many of those I'm going to use, what kind of coefficient we're going to use. Great. See, Nick, it's related to yesterday's question. Remember you were like very worried about we don't know which vector space we're going to use, and today we're going to build one. We know exactly which vector space these generators are act on, at least for the case of SU2. All right, so, but see for SU2, it's particularly happy that we have 2 of them. And if you look at that eigenvalue equation, the overall normalization doesn't matter, right? It just come out to be part of the constant. So really, I'm looking at the linear combination of J1 plus AJ2. And this is something that I hope to be, well, it gotta be that one of my eigenvectors. So now we're solving this eigenvalue problem. This is our Catan algebra. And we're going to use it to act on this guy and see what happens. Now we're looking for what kind of linear combination will make it turn into an eigenvector. And from past experience of quantum mechanics, you probably already know the result. But nevertheless, this is not a hard calculation at all. We're just going to use the Lie algebra and calculate it. And we're going to do this for SU3, which has 8 generators, so have fun. That will be Monday's tutorial. Okay, I'll do the simplest one. So J3 and the 1 that give you IJ2. And then J3 and the 2 will give me a minus AJ1, right? That's just the commutator. Says if it's cyclic, then it's I. If it's the other order, then it's minus I. And I demand this to be equals to lambda times itself. And then this is a matter of equating, compare the coefficients as lambda should equals minus IA. If I compare G1's coefficient, and if I compare J2's coefficient, it says I should equals to lambda A. Okay? And then if we plug this guy into this guy, this really gives me A squared equals minus 1. So, A equals plus minus I. So, this should remind you of these G plus, G minus things that for some reason, which would be clear, that the normalization is chosen to be 1 over square root 2. It's a normalization. The parent mathematician chose a different one. Then they are slightly different. So step 2 is done. We have some generators. We demand the linear combinations to form the eigenvector of the Catan subalgebra, and we found them. You might have other ideas why these guys are labeled plus minus. It's literally the eigenvalue, because if we take an A to be plus minus I, lambda is equals plus minus 1. So if you really want to be for sure, the subscript should have a 1 there. That's why it's labeled plus minus. It's labeled by its eigenvalue under the Catan subalgebra. Okay, so now we're done with step 2. What do we do now? Fun fact, just because it's something like curious to do, is that now basically we say before we have 3 generator G1, G2, G3, now we decided to organize differently. So now we have G3 act on G plus, give you G plus by construction. G3 acting G minus equals G minus, also by construction. And of course, just out of curiosity, that you wonder what is G plus acting on G minus. Why not? We have 3 generators. We already figured out the 2 commutator. We might as well work out this third one. So this is, I'm going to pull the square root 2's, 1 over square root 2's out. So it will give me 1/2. And then it is G1 plus IJ2, commutator with G1 minus G2. And this gives me 1/2. And the G1, the minus I, and the G1, G2 give me IJ3. And there's a plus I, but the G2, G1 give me minus IJ3. And this gives me J3. Well, this is basically why we choose the overall constant to be 1 over square root 2. It's just that we have a really, really nice Lie algebra. And this actually shows one of the points we mentioned. This still is SU2. It's the 3 generators. The only difference is we choose some linear combination of them. And hence, it says, yes, you can, like, of course, the structure constant of this Lie algebra in this basis, the J3, J plus, J minus basis, is not going to be the same as that one. It's not epsilon 1 ijk anymore. But they are still describing the same Lie algebra. Actually, in today's tutorial, you're actually going to say, because we are changing the basis of the generator, which related to what we have talked about, which is the equivalent representation. You can see the representation you find from that by writing the adjoint representation, and from this by using the highest weight method. When the dimension is the same, they are actually the same. And they are exactly related by the similar transformation that change from one base to the other. Okay. All right, now we have the Lie algebra in the format we want, which is this. So we are ready to move on to step 3. Step 3 says, let's build this vector space. Well, so this Hilbert space should have some eigenstates. And the reason we want simultaneously diagonalize some maximum set of them is, of course, we're going to choose the eigenstate to be the eigenstate of these special ones. So, and this might remind you things that we claim such J3 has some eigenstate that we call it M, which is again labeled by its eigenvalue. So we claim there must be some eigenstate that the J3 acts on gives M. We don't know what M is, but since it's a good observable, we observe and such a state exists. Okay, now we're going to study which vector space this state is going to live in. To do that, we're going to ask a question. Says, if I act on a J plus some other operator I have in hand, what would be the eigenvalue of this guy? So this is a new state, and I wonder what is its eigenvalue. Okay? So then, well, this is something we're going to use the fact that we have our new commutator and write this as this. Okay, let me finish this and we'll stop. So this gives me J plus, and this J3 acting M by definition gives me M. So this gives me M plus 1, J plus acting M. I'll use parentheses. So this tells us if I act J plus on M, that will give me a state that has eigenvalue M plus 1 under J3. Okay, any questions so far? We have no idea what M is, but now we know something more about this state M, is that if we act J plus operator on it, then we will yield M plus 1 state. That basically tells us the state M and the state M plus 1 should be in the same vector space, because we're just using these operators and we are already moving between these states. So they should belong to the same vector space. Okay? So if we have basis M, we should include M plus 1. Well, with some catch. This really was telling us is the G plus acting M is proportional to M plus 1. And then we'll hunt down this proportional constant later. Okay. So we find a basis vector in this vector space. And the reason we want to go through the trouble to organize the other operator in terms of the eigenvector of the subalgebra of Catan is that these operators will allow us to find the other base vectors in our vector space we're looking for. Right? Okay, since it's not a hard calculation at all, I'm just going to say, look, I can just add the minus in too. If there's a minus here, there's a minus here, here, and there's a minus here, here, and there's a minus sign here. Ha, there's also minus sign there. Wrong. Minus sign here. And that's the minus sign here. And then there's minus signs there. So since this is so nice, for the J minus, I don't have to repeat my calculation. I just look through the calculation I've done and adding a bunch of minus signs, and I convince myself J minus will bring the state M to M minus 1. So this is like a ladder. We decided to start from some state M. And what we show is that we can use J plus operator to hop to the next state, M plus 1. And then we can keep hopping and keep hopping. And then we can also use J minus operators to come back to M minus 1, for example. And then keep hopping and keep hopping down. And then, of course, you can hop back with J plus. Oh, here we go. with assuming that one eigenvector exists, we find all the neighboring eigenvectors that they should all form a nice vector space together because they are all related with all these operators acting on them. Okay, so now we have way too many eigenvectors we want. This is certainly have infinite of them. So let's demand that this thing will terminate. So the next step says in order to find a finite representation, we should say at some point G plus, we find a eigenvector J, and if X give me 0. Poof, you can't go above anymore. So this J then would call the highest weight because you can't go beyond that. Yep.
How do we know that this sequence covers all the possible eigenstates and not that there are actually more of them?
Well, because we have never said any property of M. M could be anything, right?
But for example, we could also have M plus 1/2.
Well, we can't because this is dictated by this J plus 1. You can choose M to start 1/2, but after you've chosen one, each step would only increase 1 just because this. You will have only 3 operators in town. One of them just give you eigenvalue M. And the other one of them will bring you to the state M plus 1, and then the other one will bring you to the state M minus 1. And there is no operator exists that will bring you to M plus any fraction value, for example. So this is what we're trying to do here. It says we have no idea about what value M can take yet, but we do know if we have eigenvalue M, the only other things that will exist in this vector space is M plus minus 1, M plus minus 2, M plus minus 3, and etc. Okay? And now we're saying we want a finite representation. If we want a finite representation, this is something we can do. We just terminate the series. But if we let the series go, if this never happens, it's definitely not a finite representation. So let's say this happened. Okay. So now we have to actually figure out what's the proportionality coefficients. If we look at this, this tells us that but on the other hand, we already say this guy should have bring us to something J plus 1 with some normalization constant. But then the only way that this is going to terminate is that if we find out this normalization constant is actually 0. Then we can actually terminate this series, says, I get well, we get something has the potential not to be infinite. We don't know it's a finite representation yet. We only know at least it's bounded above. Okay, so let's try to figure out the normalization constant. So this is just a convention. We choose the following convention, says that this is our convention, is that the G minus acting M will pick up some normalization constant depending on M, and it will bring the state to minus 1. Totally convention. Okay, so, but this, if we look at this expression, equivalent to say that J plus is going to give me an plus 1. Okay, so because J minus, okay, let me try to be slower. So this, I can write it as if m minus 1 G minus m, this is going to give me m minus 1 and m minus 1, and this will give me n minus m, right? But remember that G minus and G plus, okay, my fault. I should have emphasized after we get this step, we realize G plus and G minus is adjoint of each other. Just because that. And the G1, G2 are Hermitian. Okay, now the argument works as I can understand this expression as J minus acting on M, but I can also understand this statement as J plus acting on the M minus thing. And this should give me something M, which the something has to be the normalization of M such that these two things viewed from grouping these two together yield the same result as consider it as J plus acting on the left. So this will give me the J plus acting on M minus 1 is an M to M. And if I choose M, if I just shape M to be by 1, then this is where I get this expression. So this is a choice, and the next line is not. The next line is derivable that it has to be this. Okay, so now let's look at, well, the next step we're going to look at is this guy. So now we're trying to relate this normalization constant to something such that we can actually solve it somehow. We already look at what happens if, look at some matrix element of G minus, some matrix element of G plus. We might as well look at this. Well, this is boring because that's what we choose, it's M. That's not going to help us. Let's try to introduce this normalization somehow back in game. That we're going to use our commutator relationship and get this guy. So this will be J plus J minus acting M minus J minus J plus acting on M. And remember, this is just the adjoint of this. So this is really the square of this state. And this is really the square of this state. But we already have our normalization up there. So this is an M square minus an M plus 1 square. So by examine this guy, we find a recursive relationship says that M is equals to an M square minus an M plus 1 square. Okay. So to solve, so now we just have to solve this. Well, we are able to solve this is because we know the boundary condition is we demand that the highest one is 0 so that it doesn't go above it anymore. So in order to solve this, you can either just plug this in Mathematica says R-solve this recursive relationship with this boundary condition, and Mathematica says, oh, the result is this. But for this particular one, we can actually solve it by ourselves. By writing this recursive relationship a lot of times. So I can take it to be J, because that's the last recursive relationship we're going to get. After that, we're going to hit 0. I know I can write the previous one. And then the one before that. And then we care is to figure out what is M. So we're going to write to M. And now we see, things begin to show up again. So if I just add all these things, this guy is going to cancel, this guy is going to cancel, so presume this guy get canceled somewhere here, and this guy get canceled somewhere here. The only thing we're left, on the left, is J plus J minus 1 down to M. And on the other hand, the only thing we're left is N squared M. Okay, we also have this guy, but this guy is 0. And this is something we know how to calculate. Gauss tells us how to calculate. This is equals this divided by 2. And then figure out how many elements there. So yes, we find our normalization constant. It's given by square root of this guy. And then we can even check when M equals J plus 1. It's indeed 0. Good. So we find some normalization constant. Indeed, it says, yeah, we have something called the ladder operator will bring our eigenvalue, bring our eigenvector up a stage. Well, unfortunately, the normalization constant vanished, so the series indeed terminated as we want. Okay, but now there's something really important to happen. If we look at this normalization constant, we have just emphasized this is what we want, is that the highest weight is indeed the highest weight. And when M equals J plus 1, indeed things die as we want. But there is also this part. This part says, well, we can demand the highest weight exists. But the one that happens when M equals minus J, we also have N minus J equals 0. And what does that tell us? Where did N minus J would show up according to our choice? Over here. We choose that. So it says J minus acting minus J is N minus J, so minus J minus 1. But this guy is also 0. This is crazy. We said, let's choose the highest weight. And then to solve what that gave us, that says, well, that means you also chose a lowest weight. You cannot go below that anymore. It says you can go below one state, but too bad. The normalization constant vanished. So now you have a series that is terminated by those sides, which is good. After all, we are looking for the finite representation. If you only terminate on one side, it's still infinite. But remember, we never chose to terminate both ends. We only require to have a highest weight, and the lowest weight exists is what it hands to us. This is amazing. This also tells us something else. So suppose I start with the highest weight, and I step down to get to the next guy, and step down, get to the next guy. And then they said we can do this all the way to minus j, and then this is 0. And this says that how many steps I need to do to go from j to minus j.
2j plus 1.
Well, there are 2j plus 1 of them, then the number of steps in between would be 2j. Right, what you said is correct. So there are 2j steps, and that actually relates to the question you ask. It asks the question, says, can I take half a step? No, each step, like we can only take integer number of steps. Each step is integer. And which tells us 2j has to be integer. Because this tells us we have 2j steps. If you start from j equals 1/3, for example, you would never able to reach minus 1/3 because the distance is not an integer. So that explains why, well, that combines with yesterday's optional part of the tutorial, relates the particle property and the SU2 representation, tells us why the spin is always a half integer. Because when we solve the representation of SU2, this is what we get. It is a half integer. So now we're done. We find all the irreps. We can choose j equals 0. That gives us a singlet. So now it says you can just choose j to be something. Then we will get the corresponding representation. Okay, so j equals 0 gives us a singlet, which is pretty boring. We have one state, so nothing really interesting happens. But then let's examine j equals 1/2. That tells us we're going to have two states, which one of them is 1/2, the other is minus 1/2, which, to be not confused by the future states that have higher highest weight, that it could also happen. So normally we'll relabel this as it has the highest weight 1/2 and it has, but itself, the eigenvalue is 1/2 or minus 1/2. So you will label the state J and M, just as you did in quantum mechanics. So now, these two states, we will form our vector space. So our vector space has two basic vectors. One is this guy, and one is that guy. So next step will be writing down the representation. For J3, it's very simple. J3 says that I have eigenvalue 1/2 and eigenvalue minus 1/2. So this matrix is slightly weird. Normally, matrix element is labeled by, here I have a matrix. I have row 1, column 2, and such and such. And this matrix is weird. It says I have a matrix J3, and I have row 1/2 and the column 1/2, and this number is 1/2. Just because that this m's could be half integers, So and the row and the column are labeled by this eigenstates. So you will have some interesting labeling of your matrix. But okay, so as another example, we can work out what's, say, the matrix element of J plus under this state. So we can even do this in general. Says, what happens if I have a matrix, if I want to calculate the matrix element of J plus? And then according to our normalization, this gives me n of m plus 1 acting on m plus 1. And then I can pull the constant out, and it says, well, these two guys had better be equal. So according to this recipe, you can literally write down what's J plus in any dimension you want. You can also write down J minus in any dimension you want. And if you want to go back to the J1, J2 basis, you can also do that. You can just linear combine them, and you get what's J1, J2 in the matrix representation in this particular basis. So now we're done. Now let's introduce some terminology. This is a 2 by 2 matrix, and the thing we just studied happens to be called SU2. So this is known as the fundamental representation. This is one, the dimension of the vector space agrees with the defining matrix. So remember, SU2 is defined by all the 2 by 2 unitary matrix that has determined what. And if we happen to find a 2 by 2 representation, then it's called the fundamental representation. So if you look for your Lie algebras representation in 2 dimensions and exponential it, you're basically saying, well, SU2 is matrix after all. Then you can use the matrix to represent themselves. And then J equals 1 will give us 1, 0, minus 1. And this will curiously have 3 states. And if you recognize the following fun fact, 3 is 2 squared minus 1. And this tells the number of the generators. So in this state, the number of the generators agree with the dimension of the representation. And this is our adjoint representation. So this afternoon, we'll have a fun exercise trying to find the adjoint representation by using the method of using the structure constant. And you can also write down the adjoint representation according to what we just said. You can just find the vector space and find the matrix element of the generator. And then you can prove that they are indeed related to the similar transformation, so they are actually the same, to our delight. Okay. So I guess we'll have a very short class. Any questions? I really don't want to say anything else besides SU2 because I want to burn this process into your head. And we'll do it again this afternoon. Yes?
Is there any point where we require that the eigenspaces are one-dimensional? So that there is, we require that there is some m, such that
right.
J3m is...
Oh my God, this is such a good question. I'm so excited. Because that's what we were going to do in the last lecture. It happens to have one eigenvalue is because we only can simultaneously diagonalize one thing. when we go beyond SU2, when we have rank, so let's say 2, then you would indeed, you have to use 2 things to label the eigenstate. Yeah. That's exactly what happens in the last lecture. You would have to use more than 1 number to label your state because you have more things that the more Hamiltonian that you can simultaneously diagonalize. Yes.
This may be like implied by what you just said, but so see on the top right,
Yeah.
where you're organizing the rest of the generators using that concrete.
Yeah. Yeah.
So if you have more than 1 in the Cartan subalgebra,
Right.
like, and you have say more than 1 outside of the Cartan subalgebra, right?
Right.
Then how do you how do you do this process? Because this process really kind of like define, you had 1 element in the Cartan subalgebra, and you wanted to find like its 2 eigenvectors, right? But like, how do you know like which, like
you actually,
which one?
So basically what happens is then you're looking for, say, some guy labeled by its eigenvalue. So you're looking for a generators that has 1 eigenvalue under the first member and another value under. So you actually find the eigenvector that are simultaneously eigenvectors for all your numbers of the subalgebra. Okay. And this is doable, and we're going to do it for SU3. So that's
why is that always doable?
Why that is always doable.
Oh, right. Never mind.
Because,
they mutually communicate.
Right, yeah. Because they mutually.
Yeah. Okay. Yeah.
That's the simultaneous diagonalization process.
Yeah. Okay.
Yeah. And we're going to do it on Monday for SU3. Well, you would think it's pretty crazy, to do linear combination of all the other 6 generators. But hopefully, just by observation, you will see some of them are more promising than the others. Okay. Yeah, very good. See, this question leads to why the SU2 is more powerful. So basically, what we do with the rest of the Lie algebra is to find the SU2 subalgebra in all the other Lie algebra. And then we can use the same method, except for the the important catch you guys both emphasize is that we'll have to label our state with more number of things. Okay, and doing that, we'll have some miracle, and then that's how the mathematician realized we can actually classify everything. And we'll learn everything in the last lecture. Very good questions.